Today I want to talk about engineering and engineering research specifically and how it fits into the broader scientific context. So I'll start with going over just briefly. I went over the other day Karl Popper's idea of what is good science, what is a scientific process, and from there we'll branch off to see how engineering fits using that same framework. So to start with, in Karl Popper's view of things, you have theory, and he doesn't go into much detail about where theory comes from. It's like any sort of creative inspiration. It can come from anywhere, but once we have some ideas about the world at large, he actually calls these universal statements. So not specific claims, but claims about the way things are always and in all places. So these are candidates to be laws as we think of scientific laws. So we have these set of hypotheses. Then we have some initial conditions. And what we're building towards is we're going to use a combination of these hypotheses and these initial conditions, which are simply established observations. So claims that we already accept as true about the world. And we're going to combine those in order to bring ourselves to make some predictions, which then we can attempt to falsify by experimentation. This is the overall process as described by Karl Popper. So we'll put this in here. We have some predictions. We're going to draw our connection here. So we're combining these here to get these predictions. And then we are going to design an experiment which will yield some observations of reality. And we're going to compare these two. We're going to compare the predictions we've made with the observations that we've now made by means of experimentation. If these tend to contradict, well, then we're going to revisit our hypotheses. We're going to revise them or throw them out and start anew with some other set of hypotheses entirely. And this is the overall process and the way that science advances. And it is important to emphasize here that this process, going from the hypotheses to the predictions combined with the initial conditions, this is a deductive reasoning process. So you have a premise and a conclusion. We're not using inductive reasoning, which is where you say, well, this has worked every time, therefore it will work again. The reason this is important to make this distinction is because in engineering, this becomes a key difference. Because once you have a set of hypotheses, or say scientific laws that are well established, that's where engineers start their work. They start from the established theory, and they are going to infer by inductive reasoning that because this has stood up to scrutiny so far, that it's going to work. And so we use that to design our machinery or whatever else we are doing. Of course, at the end of the day, testing is necessary in engineering. You would never design a machine and then just start using it before you would ever tested it. But now, there's this peculiar thing that we would call engineering research. There are engineering academics who are professors in universities, just like full scientists, pure scientists, and they're doing something that's vaguely scientific, but also somehow engineering. So let's erase those lines so we can add in a step. So one key step that is missing is a set of assumptions. So in general, in engineering, we are going to go towards a model. I'm no longer simply calling this a prediction, it's a model. We're starting from our theory, our hypotheses, and this still is a deductive reasoning process, and we filter them through some assumptions to come to some model, which is a subset of the overall scientific theory. And this model is what we can then test. But notice here, if we now do our test, we design an experiment, make some observations, if these two things no longer match, we haven't falsified the entire scientific theory. Likely what we've falsified is the assumptions. And so this is critical. This is the difference between pure science and engineering. In the scientific endeavor, if you're trying to test a theory, you're going to avoid as much as possible any ad hoc assumptions for this exact reason. Because if there's a falsification here, it doesn't necessarily track back to a falsification of the original hypotheses. It could just be a falsification of the assumptions. And so it's also critical to make sure you are always clearly stating what your assumptions are, because if you made an assumption and you haven't acknowledged it, then when things go wrong, you have no idea why, and you're just standing there scratching your head. So this is a key difference is between pure science and engineering, is the assumptions we are making in order to get what we will call models, which are subsets of theory that have specific practical application and in general are much easier to use. They're mathematically simpler than the overarching scientific laws. That brings us to consider, what are we testing? So we've made some assumptions. So in theory, the scientific laws are infinite in scope, in time and space. And once we've added some assumptions, we have now made a model who has some restricted domain of validity. So there are certain conditions under which we expect the model to be valid, and other conditions under which we don't expect it to be valid. But of course, I've drawn this as a line, but let me make this fuzzier. The reason is we don't necessarily know exactly where these boundaries are. So in my own field, for example, in fluid mechanics, one common assumption we are forced to make is that viscosity and its effects are negligible. So in the governing equations, we simply set viscosity to 0 everywhere, which simplifies the math considerably so that we can simplify the equations to a model that applies in cases where viscosity is indeed negligible. But any normal fluid, in normal circumstances, has some finite amount of viscosity. So how little is little enough? When we say how valid is the assumption, it's not strictly true, but we might say it's valid, meaning it's true enough. But we don't in advance necessarily know exactly where these boundaries of our domain lie. So if we are now designing an experiment to test this model, what we're doing is not exactly trying to falsify it. So this is where it is distinct from the scientific endeavor. So we might do a test case. This is a sort of sanity check where we do a test case right smack in the middle of where all of our assumptions we believe are the most valid, most likely to be true. And if this turns out to be false, we're kind of starting from the drawing board, because if all of our assumptions and all of our expectations are now being falsified, we've done something wrong, or our assumptions are simply poor. We can do another sort of sanity check out here, where it's way away from where I expect it to be valid, and this is another sort of sanity check, because if it works, this is still more useful than the other tests, because if it works, even where it's not expected to, that's sort of fortuitous, but not terribly useful, because it could be a fluke. And as engineers, we don't want to depend on some sort of fluke. So if something works, we want to know why it works, usually so that we don't believe we just got lucky. Because if we got lucky once, we could get unlucky as well. And then I think what the best type of study we'll do is to try to explore the space in between. So we're going to explore and essentially probe where exactly this boundary is. So where does the model start to break down, where it becomes unacceptably inaccurate? It's never going to be perfect, but how acceptable is acceptable enough depends entirely on the application. But you're going to design an experimental campaign that's not simply trying to falsify the model, but actually bridge the gap between where the model is corroborated and where we expect it to be falsified. And of course, this could be a multi-dimensional space, so there's many different parameters that go into your model, possibly, and so you'll be doing this around all the borders. And you're limited then, of course, simply by practical concerns about how many experiments you can do. It may well be a perfectly valid engineering research contribution to do simply one test right in the middle or somewhere else in this space, if that experiment happens to be very, very difficult to do and there's no other way to get our answer. So that's my general overview. The key differences I see between scientific research and engineering research is that we're no longer in the realm of trying to falsify things, because for the engineering practitioner, we're not eschewing inductive reasoning, we're actually embracing it thoroughly. And so we are now trying to provide enough evidence from which an engineering practitioner can confidently apply a model through inductive reasoning, saying, okay, this has been tested many, many times. I believe it's going to work. I can invest some resources in actually designing whatever process or machine you are worried about. Now, I'd like to add one other thing, that when I was feeling this idea out of what to say about this topic, an engineering colleague of mine summed up the engineering profession, I think, quite nicely. He said that engineering is simply a collection of processes that allow you to say that an idea is not a terrible idea. that's about as good as you get in some sense, because engineering problems become much more complicated than the simplified types of experiments we do in the scientific realm. Again, this goes back to, we're trying to eliminate all assumptions if we're doing a scientific model, so that there is nothing to be falsified except the original hypotheses. In engineering research and the development of models for practical use, we are intentionally making assumptions and then probing the space within those assumptions and where we expect them to be valid, and then putting that forward for a practitioner to be able to use his inductive reasoning to apply it with confidence. And I'll leave it at that. And if you have any comments, please leave them below. Thank you very much.